It is now my very great pleasure to introduce to you our speaker, our president, and my friend, Professor Stephen Barr, who is Professor Emeritus of Physics at the University of Delaware. He got his PhD in theoretical particle physics from Princeton in 1978. He is a fellow of the American Physical Society since 2011 for his contributions to grand unified theories, the theory of CP violation, the asymmetry between matter and antimatter in the universe, and the cosmology of the early universe. And of course, he is president and founder of the Society of Catholic Scientists. He is the author of several publications, including the book Modern Physics and Ancient Faith, which I highly recommend to you if you are interested in the relation between those topics. By way of personal introduction, the first time, some of you know this story, but the first time I met Steve was at the Supersymmetry conference in Seoul, Korea in 2008. Our mutual friend, Professor Xavier Calmet, also a Catholic scientist, introduced me to Steve. And since my family is from Korea and I'm familiar with Seoul, the first question Steve had for me was, where can I go to Mass on Sunday? And so I pointed him to the beautiful Cathedral of the Immaculate Conception in the Myeongdong district in Seoul. And I hope you found your way there and got to Mass on Sunday. To my memory, at the time when Steve met me, you pulled a list out of your pocket and added my name to it. Steve had this secret list of Catholics, in physics and maybe other sciences. So he took my name down. I had no idea what was going to happen to that list. I figured when the persecution came and they found Steve, they would find me too. And that would be fine with me. But then I learned about 7 years later that Steve emailed everyone on this list you had compiled, I suppose, to form the Society of Catholic Scientists. And that's how I got to be involved and got to know about the SCS and in its events. So that Sunday Mass in Korea in 2008 has led somehow all the way to you being here tonight to tell us about whether the universe is made for life, anthropic coincidences, and ideas about the multiverse. Steve Barr.
Can you hear me okay? Good. Thanks, Chris, and thanks all of you for coming out to hear me. So let me just make sure I can find the buttons here. Yep, I can. All right, so is the human race meant to be here? Or are we just a fluke in a meaningless universe? There are two very widespread and diametrically opposed views on this question. One is held by Christians, Jews, and many other theists, and the other is held by most non-religious people, including atheists. What is the Christian view? According to Scripture and Christian tradition, we definitely are meant to be here. And the human race has an important place in the divine plan. The letter to Diognetus, for example, a Christian work of the early 2nd century, said, God loved the race of men. It was for their sakes that he made the world. The first creation account of the book of Genesis culminates in the creation of mankind. And the Apostle Paul told the Ephesians that they were chosen by God and destined to be his sons and daughters, quote, before the foundation of the world. On the other hand, many atheists tell us that science has shown that the human race is just an accidental byproduct of blind material forces in a universe that has no point or purpose. Bertrand Russell, for example, said that man is, quote, a curious accident in a backwater of the universe. A classic statement of the atheist view was given by the physics Nobel laureate, who died just a year or two ago, Steven Weinberg. In his 1977 bestseller, The First 3 Minutes, A Modern View of the Origin of the Universe, he famously wrote, "It is almost irresistible for for humans to believe that we have some special relation to the universe, that human life is not just a farcical outcome of a chain of accidents, but that we were somehow built in from the beginning. It's very hard for us to realize that the entire Earth is just a tiny part of an overwhelmingly hostile universe. The more the universe seems comprehensible, the more it also seems pointless. Now, Weinberg's view is understandable. The universe is indeed inconceivably vast compared to the Earth and its inhabitants. The human race is indeed the outcome of a long chain of events that could have gone otherwise. The forces of nature, while not literally hostile to us, certainly are blind, unfeeling, and often harsh. The universe goes about its business without any concern for us. Isn't it foolish then, as Weinberg said, for us to imagine that we were somehow built in from the beginning and meant to be here? Hasn't the whole thrust of modern science since the time of Copernicus, for the last 4 centuries, been away from such naive anthropocentrism? Hasn't the story of science been about the successive dethronement of man, as Stephen Jay Gould, the famous Harvard biologist and popular science writer, was fond of saying? Well, maybe not. It's beginning to look very much like perhaps we were built in from the beginning after all. In the last 50 years or so, physicists and others have begun to recognize, begun to see that many features of the fundamental laws of nature and the structure of the universe appear to be just what is needed for the existence of living things to be possible, including us. These features are often called anthropic coincidences. Why are they called that? Well, the word coincidence points to the fact, or claimed fact, that some features of the laws or of the structure of the universe happen to coincide with what is needed for life to be possible. And the word anthropic just comes from the Greek for human being. It's not the best adjective to use because actually most of the arguments are not just about the possibility of humans, but the possibility of any living things at all in our universe. So, until about 30 years ago, it was almost taboo to even discuss, mention, let alone discuss, anthropic coincidences in the physics research literature. The idea was that there might really be coincidences and that they might have any significance was often dismissed out of hand as unscientific. There are a number of reasons for this. One was expressed rather frankly by a Nobel laureate in physics who said that he hated the whole subject because, quote, it smells like religion. But there were other reasons as well. But gradually, attitudes have changed in the physics community, in part because a number of leading physicists, including Steven Weinberg, as a matter of fact, began to take anthropic coincidences seriously as calling for explanation. It's now fairly widely admitted among particle physicists that some of these coincidences are real and may be telling us something important about the world. For example, the late Stephen Hawking, in his final book, which he co-authored with Leonard Mlodinow, called The Grand Design, he wrote, "What can we make of these coincidences? Our universe and its laws appear to have a design that is tailor-made to support us, and if we are to exist, leaves little room for alteration. That is not easily explained and raises the natural question of why it is that way." Edward Witten, regarded by many physicists as the most brilliant theoretical physicist in the world, and who is not religious himself, he's called himself a skeptical agnostic, on religious questions, said this in an interview. He said, "The laws of nature are very delicate. The fact that galaxies, stars, and planets roughly like ours could have formed, and that living things roughly like us could have formed, depends on many details of the laws of physics as we currently know them, being just the way they are and not being slightly different." I think we'll never resolve the sense of wonder about that. Okay. Now, before getting into the question of the possible significance of anthropic coincidences, it may be helpful to give some examples of them. Those who want to see a more in-depth discussion of some of these can refer to a number of technical physics papers as well as several popular books written by physicists. Okay, and I give a list there, but you're not going to be able to memorize all that, but I can give it to you afterwards. Now, a famous anthropic principle, by the way, that word slipped out. I don't use the term anthropic principle. It's that. A famous anthropic coincidence has to do with the so-called strong force, which is one of the four basic forces of nature that we know about, five if you count the Higgs force. It's the force that holds atomic nuclei together. The four basic forces are electromagnetism, the strong force, the weak force, and gravity. Now, if this strong force, which as I said binds the protons and neutrons or nucleons together in nuclei, if we're only about 25% weaker, we wouldn't be here. Now, why is that? Because it takes many types of atoms to build a living thing. I am told by a biochemist that there's 25 different chemical elements needed to make a human body. Now, where did all these elements come from? Well, in the very early in the history of the universe, right after the Big Bang, there was basically only hydrogen and helium. Most of the stable elements, heavier than that, were formed by astrophysical processes taking place inside stars. And the way it happened well, let me give you an example. Well, first of all, early in the universe, very early on, all you had were protons, as far as ordinary matter is concerned, protons, electrons, and neutrons, and some neutrinos. Now, therefore, the only nucleus you could have right after the Big Bang was a nucleus consisting of a single proton. And that gives you a hydrogen atom, and there is sort of a child's view of a hydrogen atom, an electron going around a proton. Now, to make the heavier elements than hydrogen, you have to start sticking protons and neutrons together to form larger nuclei. Now, the first step in that process, you see at the top left, where a proton, which is sort of blue, and a neutron, which is depicted as yellow, get together, stick together to form something called deuterium. Then a neutron can come along, and one's coming up from the bottom, and sticks to that to form a three-particle nucleus called tritium. And then a proton can come along and stick to that and form a helium-2 nucleus, also called, for historical reasons, an alpha particle. Then that kind of thing keeps going on, smaller nuclei sticking together to make bigger nuclei through nuclear fusion, till you get things as large as uranium, which has 92 protons and over 140 neutrons. Now, the crucial point is that if the strong force were only about 25% weaker than it is in our world, the first step in all of this wouldn't happen. That is, a proton and a neutron would not stick to form deuterium. So the first step in the ladder wouldn't happen, and you wouldn't therefore be able to build up any of the heavier elements either. You'd be left with a universe that only has hydrogen. And you can't I don't think many people think you can make a living thing if all you have to work with is hydrogen. Now, okay, so what would have happened if the strong force had been a little stronger than it is in our world? So there's a disaster if it's significantly weaker. It turns out that if the strong force were only a a very tiny bit stronger, about 1% or a few percent stronger, it would actually also probably cause a disaster as far as the possibility of life, because then it would have been strong enough to bind together 2 protons, which cannot happen in our world. And if 2 protons can fuse, that would radically change the way stars burn like the sun, burn their nuclear fuel. And it is very doubtful that you would have the right kind of stars to be able to support living things, to provide the energy for living things. Though that's a more complicated argument. So the strong force might be in a sweet spot, not too strong and not too weak. So that's a very famous example. Another famous example of an anthropic coincidence. Another famous example concerns the way carbon is made, and was made in our universe. Back in the 1950s, I believe, it was an astrophysicist named Fred Hoyle was thinking about how carbon could be made. And it turns out it has to be made in the following way. You have to have 3 helium-4 nuclei, or alpha particles, as they're customarily called, collide simultaneously in a 3-way collision. They will stick to form carbon-12 and release some energy. Now, why do they have to have 3 of them collide? Well, if you had only 2 alpha particles collide, they don't stick. Well, they'll stick for a very brief moment of time, about 10 to the minus 16 seconds. Okay? And then to form this highly unstable beryllium nucleus, and at 10 to the minus 16 seconds, they fly apart. But if a 3rd alpha particle comes along in that sliver of time and hits them, the 3 can fuse to form carbon. And that is how the carbon in the universe is made, in the interiors of stars, which burn helium to make carbon. Now, Hoyle realized that this process, as you can imagine, is kind of rare. And therefore, his first estimates were that it would produce far less carbon than we actually observe to exist in the universe. And he puzzled about this, and he realized that you wouldn't have produced any significant amount of carbon unless somehow this process was enhanced. And it turns out to be enhanced because this fiery ball in the middle, this carbon-12 nucleus that's formed, has an excited state, or resonance, at exactly the right energy to resonantly enhance this process and make it go much more readily. If that energy level of the carbon-12 nucleus were just a percent or 2 higher or lower in energy, this would not have been enhanced, and there'd be very little carbon or elements heavier than carbon in the universe. And as we know, all life that we know about is based on carbon, so that would have been a disaster. So this energy level is just right, placed in exactly where it needs to be to make it possible to have carbon, a significant amount of carbon, and therefore life. That's a very famous anthropic coincidence. And I can go on giving you other examples. One that was pointed out, one that was pointed out by myself and 3 collaborators, had to do with a parameter in our standard, what's called the standard model of particle physics, a parameter called V, little v, which has to do with the Higgs field. It has to do with the Higgs boson. And this parameter V, which stands for vacuum expectation value of the Higgs field, turns out it has to be in a very narrow window of all the sort of allowed range that it could mathematically be. It has to be in a very narrow window if we're to be here. And I will, so why is that? Well, I'm going to go into a little detail on this. It turns out, just a little detail. It turns out that if V were significantly larger than it is observed to be in our world, then a number of disasters would occur, depending on how much larger V is. But if V is not just a little bit larger than it is observed to be in our world, neutrons would be unstable, completely unstable, even inside atomic nuclei. Okay? And which means that all the neutrons in atomic nuclei would decay into protons, which means nuclei would have to be made not of a combination of neutrons and protons, but just of protons. And it turns out you can't make stable nuclei just out of protons. And so that's one disaster that occurs. If B is much smaller than it is observed to be in our world, then a very different disaster happens, and that is that a subtle quantum mechanical process called Spalaron processes, which happen very rarely in our world, would happen very readily. And these processes would actually erase all of the protons and neutrons in the universe. It would erase all the baryons. And there would be no matter. There would be no atoms at all of any sort. So this parameter V seems to be in a sweet spot as far as making life is concerned. Okay. There's a lot more to the story of this parameter than I'm going to tell you, though. Now, these three examples I gave you all have to do with fine-tunings, as they're called. Some parameter has to have just the right value. Okay. The strength of the strong force, or the value of V, or the energy level of the carbon-12 nucleus. But not all of these anthropic coincidences have to do with fine-tuning. Some of them are gross qualitative features of the laws of physics or the structure of the universe. For example, and many examples of this could be given, the fact that the physical world is based on the principles of quantum mechanics is really important. Quantum mechanics is weird, but it's also very good, okay, from the point of view of us being here. For example, the very fact that matter is made up of particles, quantum mechanics tells us, roughly speaking, that the world is grainy. It has a sort of grainy structure. The very fact that the world is made up of particles at all, like protons and neutrons and electrons and so on, is due to quantum mechanics. Moreover, the fact that those particles, you can build stable structures out of them is also due to quantum mechanics. So for example, why isn't it the case that all the negatively charged electrons in atoms, why don't they get sucked into the positively charged nucleus? In which case matter would catastrophically collapse. Well, it's because of the quantum mechanics. Electrons, because they behave quantum mechanically, cannot be sucked into the nucleus, as it turns out. Not only that, but in a classical world, that is a world based not on quantum mechanics, but on more intuitively reasonable seeming classical physics principles. An atom, the electrons would have infinite number of ways of orbiting the nucleus. An electron could go in very elliptical orbits or circular ones, and in a multi-electron atom, there would be an unimaginable variety of ways that the electrons could be orbiting, so that a single atom would not behave the same from moment to moment. And no two atoms of the same element would behave the same. I mean, matter would be constantly morphing and be protean and constantly, you wouldn't be able to build stable structures. So the stability of matter is really, and the ability of matter to form complicated structures is largely due to the principles of quantum mechanics. Well, the fact that the world has three large space dimensions, could have other space dimensions, but if it does, those are probably of subatomic size, not. But the fact that the number of large space dimensions is 3 is also kind of important. If the number of space dimensions were larger than 3, Newton's law of gravity, the inverse square law, would be different. Instead of the force depending on the gravitational force between two particles depending on the inverse square of the distance, as in our world, it would go as the inverse d minus 1 power of distance, where d is the number of space dimensions. So in a 4-spatial dimension world, the gravitational force would go as the inverse cube of distance, and so on. So it turns out, and it's actually very easy to show, that in a world with more than 3 space dimensions, assuming the laws of gravity are otherwise the same, the gravitational force would be stronger at short distances and weaker at large distances, meaning that planets could not stably orbit stars. They would either, they got close, they would plunge into the star, or they would fly off into space. They couldn't stably orbit. They can in 3 dimensions. What about if there are fewer than 3 space? By the way, it would be the same with atoms. Electrons would not stably orbit nuclei. They would either plunge in or they would fly off. What if there were fewer than 3 space dimensions? Well, then it turns out there would be a number of problems. It'd be hard to have complicated circuitry. Imagine trying to draw a complicated circuit diagram on a 2-dimensional piece of paper. Wires have to go through each other, and they would be short circuits. Whereas in 3 dimensions, wires can go around each other, or neurons, or axons, can go around each other. So you can build more complicated circuitry, as would be required for a brain in 3 or more dimensions. Oops, I think I pushed the wrong, there we go. I think I just, wait a minute. Here we go. I actually skipped that because that had to do with the Higgs field, and I'm not going to go into that. So here's a famous little math puzzle that you give kids. There are 3 houses, and there are 3 utilities. And the question is, can you link every house with every utility in a way where the links don't cross? And it turns out you can't in 2 dimensions. And there is the yellow line crossing the blue line. Something's going to intersect. So you're limited in what the complexity of circuits that you can draw in 2 dimensions. So again, 3 dimensions is very, very special. So it's fortunate that the universe has 3 space dimensions. Okay. Now I've given a number of qualitative features of the universe and some of the fine tunings, but there are many other examples. I remember when I quoted both Hawking and Witten, they both refer to many features of the laws of physics that need to be just the way they are, or we wouldn't be here. And that's really quite remarkable. Now, what is one to make of these coincidences? Well, one rather obvious possibility is that the mind that framed the laws of nature did so with the end in view that the universe should give rise to living things. And that's a perfectly reasonable explanation. But there's a perfectly naturalistic way of explaining at least some anthropic coincidences. And that idea, which is very speculative, is called the multiverse idea. Now, a lot of religious people think that the multiverse idea, well, what is the multiverse idea? The multiverse idea is not, as many people necessarily mean, that there are many universes. It doesn't have to mean that. Nor is it necessarily connected with something called the many worlds interpretation of quantum mechanics. The most conservative kind of multiverse idea, the simplest, most conservative version of the idea, is that the universe, 1A, is very big, much bigger than the part we can see. And B, in the parts of the universe that are too remote for us to see, that are outside what's called our horizon, outside what's called the observable universe, that in the very distant and unobserved parts of the universe, conditions are very different. So different that, at least superficially, it looks like those regions have different laws of physics. In those other parts of the universe, perhaps you don't have an electromagnet. In some of the regions, you might not have electromagnetism. In other regions, you might not have the strong force. Or you might have the strong force, but the strength of it might be greater or weaker, weaker or stronger than in our part of the universe. Or the parameter V might take different values in different parts of the universe. Now, if this were the case, if the universe, so that's what we mean by a multiverse. What makes a universe, it's a kind of universe. What makes a universe a multiverse is that so the idea of most physicists is that there's really one universe, and that deep down that one universe has, at the deepest levels, one set of truly fundamental laws, sort of the bedrock laws of the universe. But that those laws can manifest themselves in such a way at a more superficial level that things look so different that you might think the laws were different in different places. But deep down, they're traceable to one set of truly fundamental laws. Maybe an analogy would be water and ice look so different that a naive person might think they're completely different substances governed by very different laws, but deep down, and they are in a sense, but deep down they're all both made of H2O and governed by the same laws of chemistry and physics. So that's the idea of a multiverse. Now, if you had a multiverse, you could imagine that it would explain some anthropic coincidences. So take the one where the strong force is just right to make life possible. Well, that may be because the strong force takes all possible values at some place in the universe. It's a big lottery. In some regions it's stronger, in some other regions it's much weaker. And if it takes or a lot of possible values throughout in different parts of the universe, it's very likely, if the universe is large enough, that there'll be some places where it has just the right value for life. And you just apply the same idea to all the other parameters that seem fine-tuned. The parameter V could take different values in different places. And so if the universe were large enough, it could be that all these parameters that need to have special values to give rise to life, that there is some region where they all have just the right values, by just the luck of the draw. You buy enough lottery tickets, one of them is going to win. You try enough keys in a door, in a lock, one of them will open it. Now, some people think this is just some desperate idea cooked up by atheists to avoid the obvious conclusion that the laws have been deliberately fine-tuned, as it were, to make life possible. That is too jaundiced a view. There are actually physics reasons that have nothing to do with us being here. There are physics reasons for taking the idea of a multiverse seriously. For one thing, there are very compelling reasons to believe that the universe is vastly bigger than the part we can see, exponentially larger than the part we can see. Second, we know of fairly simple theories that people study in particle physics that at least at a limited level have different, where the laws manifest themselves can manifest themselves in different ways in different places. For example, as Chris's introduction mentioned, I've worked on things called grand unified theories. If you take the simplest supersymmetric grand unified theory, it turns out that the equations have several solutions, and different parts of the universe would fall into different solutions of the equations. And some parts of the universe would have the three non-gravitational forces that we see. Another solution is that that they're not three forces, but two that are somewhat different. There are actually different ways that the fundamental laws manifest themselves, such that there are actually different forces in different parts of the universe. So the idea is not as far-fetched as it would sound to the physics layperson, and people have been thinking about this for reasons having nothing to do with us being here. So admittedly, there's no experimental evidence that the universe is a multiverse. There's not a shred, granted. But there's a further reason for taking it seriously, and that is that the best candidate for the ultimate laws of physics is something called superstring theory. It's the only known way of consistently unifying the laws of gravity with quantum mechanics. And so many theorists take this superstring theory very seriously, as people have been studying this question for over half a century and have not found any other way of combining gravity and quantum mechanics. So it's a very plausible candidate for the ultimate theory of physics. And it turns out to be such that it does manifest, it has many solutions. So if the universe is described by superstring theory, it's very likely that different parts of the universe look very, very different from each other in the way that I described. Now, so the multiverse idea has to be taken seriously. Now, I don't think that completely undercuts the idea that the universe was made with living things in mind. I don't think it completely undercuts that argument, because in a way, for the universe to be a multiverse is itself a kind of anthropic coincidence. I think that what we can say with some confidence now is that if you want the universe to have the possibility of giving rise to life, the fundamental laws have to be special in some way or another. They have to be, either they're special because various features of the laws are just right throughout the universe, are just right to give rise to living things, or the fundamental laws are special in being the kind of fundamental laws that give rise to a multiverse. It's a very strange thing for the fundamental laws to have the kind of flexibility to allow the strength of the strong force to vary from place to place, or the parameter V to vary from place to place, and so on. Fundamental laws have to be rather peculiar to give rise to a multiverse structure. So as I said, the laws of physics, the two ways of explaining the anthropic coincidences that we observe is either that they're fine-tuned or they're set throughout the universe, or that they arise as a result of a multiverse. But in both cases, you need to have the laws of physics be very special for that to happen. So I think, at least given our present state of knowledge, you can say that the evidence, at least prima facie, is that we were, or living things were built in from the beginning in the very structure of the laws of nature. So what Weinberg said when he was sort of dismissing that idea 50 years ago has really been undercut by these more recent developments. Now, there's a very interesting anthropic coincidence that I'm going to end with, and that has to do with the size of the universe. Many people throughout history have been troubled by the vastness of the universe in comparison to us, with the Earth. And it makes it look like we're somehow insignificant, you know. Even Pascal said, the eternal silence of the infinite spaces frightens me. Even in the Psalms, the psalmist talks about, you know, when they consider the moon and the stars, what is man, that thou art mindful of him? We seem to not amount to very much in this vast universe. And yet it turns out that the vastness of the universe is a precondition for our being here, if the laws of physics are anything like what we know them to be. Why is that? Well, first of all, it takes a long time. It took a long time for us to arise. Why? First, you needed all those chemical elements. As I said, you started off with just protons and neutrons and electrons and neutrinos and things. But to synthesize all the elements of the periodic table, all the ones that you need for life, took billions of years of astrophysical processes. Most of those stable elements were cooked, were synthesized in the interiors of stars by nuclear cooking. And that took billions of years. Once you have the chemical elements in place, it takes billions of years of it takes a long time to make the first living thing, but it took billions of years, it seems to take billions of years of biological evolution to produce complex multicellular creatures with nervous systems and so on. So to have living things such as ourselves, you need a universe, given the laws being like what we know them to be, you need the universe to be able to last for billions of years. Now, Einstein's theory of gravity relates the longevity of a universe to how big it gets. Suppose somebody said, you know, I think God, I don't see why he had all that wasted empty space out there, those billions of light years of empty space. That was a bad idea. If we're really the point of, at least one of the points of this universe, why couldn't he have made a universe that was just a few thousand miles across? That's plenty of room for human beings to cavort in, and you know, that's the size of the Earth, right? Well, if God had made the universe that never got bigger than a few thousand miles across, then according to Einstein's equations of gravity, it would have only lasted for a matter of hundredths of a second, not billions of years. Even if the universe were allowed to be the size of the solar system, that was its maximum extent, it would have lasted only for a matter of hours. If the universe is to last for billions of years, it has to achieve the vast size we see it to have, which is at least tens of billions of light years across. So far from pointing to our insignificance, the vastness of the universe is, as I said, a precondition, given the way the laws of physics work. It's a precondition for us being here at all. And so that itself is a kind of, you might say, anthropic coincidence. And I think that is where I will stop and take questions. Thank you.
Steve, we have plenty of time for questions. Please ask.
You pick them.
John, go ahead.
So thanks for coming to the talk. I also want to just say that as a Christian and Catholic, I don't need any evidence from science to tell me that God exists or that Christ was here. So, we don't need to go out into science and find these coincidences to have faith.
True.
And so I've got another, more statement. So, 100 years ago, maybe more now, something like the Rydberg constant was not understood.
Correct.
So we've got a field called quantum mechanics where a whole bunch of things that weren't understood then just magically come out, and they could have been no other value. It's not like we believe, at least in our part of the universe, that Rydberg constant is something else that comes from other fundamental physics. So I'll ask, maybe we got it all wrong, that your little V saying it could move this way or that way. If we get a truly fundamental theory that's something like that we can't understand, it might take all the parameters in the standard model and say, alpha needs to be this value, V needs to be that value. And then in some sense we're left with, they're not really little coincidences. There was only one way the universe could work. And it gives you your V, it gives you the strength of the strong force. And then there isn't really these coincidences. It's just, there's only one way to do it.
Okay.
And that's sort of the universe I intuitively think of when I'm a scientist studying nuclear physics.
Okay, so there are two questions there. So the first one is, yeah, we don't need this kind of thing to believe in God, and I totally agree with you. So, when St. Paul says in the Epistle to the Romans in chapter 1 that the pagans are without excuse for not believing in God because we can know that God exists from the things he has made. He wasn't talking about needing test tubes and telescopes and particle accelerators and so on. He was talking about that everybody has evidence that God exists from the existence of the created world. And if you go back to the early church fathers, when they were explaining how it is that from the physical world, there are other reasons to believe in God, but from the physical world, what are the main reasons for believing in a creator? They pointed, and I have a whole skein of quotes from about a dozen early church fathers who all are saying the same thing. There are two main ways we know from the physical world. One, that it exists at all, so they said there must be a cause of being. And second, there must be a cause of order, that the universe is orderly. It's not just some chaos, it's an orderly place. In fact, it's harmonious, it's orderly, they use all these words, mostly order, but they say also harmonious, beautiful, lawful, and so on. And that means there must be, as St. Irenaeus said, there must be a giver of order. Or if there's a law, there must be a lawgiver. So that doesn't require knowing all the details of the order of nature. It just means recognizing the world is an orderly place, and that calls for explanation. And so I totally agree with you. Nevertheless, I think these arguments are useful in parrying arguments of the atheists. So if you read my book, Modern Physics and Ancient Faith, which I heartily endorse, it's an excellent book. I say in that book that I'm not giving proofs. What I'm doing, I'm not trying to give proofs. It's not a matter of proofs. But the atheists also don't claim to prove from science that God doesn't exist. But they have historically pointed to many things about nature that they think suggest that the world is pointless, as Weinberg says, or that suggest an atheistic or a materialistic view of the world, or a view of the world in which the universe is pointless and we're not meant to be here. For example, they've often pointed to the vastness of the universe. Weinberg himself says it's hard for us to believe that we live in this, that the Earth is just a tiny part of an overwhelmingly hostile universe. It's not a proof of anything, but it's an impression people get from science. Similarly, Weinberg thought that the more we learn about the laws of physics, the more it points to us not being meant to be here. So I think it's useful for parrying those arguments to say, wait a minute. We do know a lot of things about physics now that actually seem to point in the other direction, to perhaps us actually being meant to be here. Okay? So I agree, we don't need these to prove God exists, but I think they're useful at least as a defensive arguments against many of the common arguments deployed by atheists. And I think we do need to defend against those arguments made by atheists on the basis of science, because those arguments have cut a wide swath through the population of believers. The studies have shown that the main reason given by young people for leaving the faith is that they believe that science and faith are incompatible. So we really owe it to them to show that there are things in science that point more to the compatibility and that answer the standard atheist arguments. As far as the second point, yes, it could well be that when we know the ultimate laws of physics, whatever they may be, they may show us that V has to be just this particular value, that the strong force has to have this particular value, and so forth. That would, as the famous astrophysicist Martin Rees pointed out, that itself would be an amazing fact. If, suppose you need, let's say, 20 conditions to be satisfied by the laws of physics for there to be life. The V has to be in this range, the strong force has to be in this range, that this has to be this way and this way and this way. Let's say there are 20 of them, and they happen to be exactly the same 20 conditions that you get from the fundamental theory of physics. That's even more astonishing, right? That's a massive coincidence. It's not getting rid of the coincidence. It's making those 20 individual coincidences into one gigantic, astonishing coincidence that the 20 conditions you needed for, because that's what the mathematics of, say, some ultimate theory tell you, and also they happen to be exactly the same 20 conditions that you need for life, that they correspond to each other perfectly. That's itself a massive coincidence. So that's all I'll say about that. Yeah.
What do you think with the argument that Paul gave? He's thinking that it could be just that we're all a simulation. This is a simulation of everything.
Well, that is a sort of an infinite regress, doesn't it? I mean,
You may want to repeat the question.
oh, Paul, somebody suggested we may all be living in a simulation, sort of like in the Matrix or something. I've never seen what that buys you, because, you know, then the simulators, are they also a simulation? And then so on. You can't have so there's presumably not an infinite regress of simulations. So whatever you can make, so you go to the people who really exist, and the rest of us are simulations. You go to those really existing people, and you ask all the same philosophical questions of whether they were meant to be there, why they're there, and so on. Yeah.
I was at Caltech in 72 and 74, and interested enough, I was working in Willie Fowler's Kellogg lab, working on nucleosynthesis.
Right.
And the carbon cycle and the silicon cycle were two key elements that we used to try to make cross-section measurements are to feed into the differential equations. But I have never realized, and it's astounding to me, that if this strong force were maybe 4 or 5 or 6% stronger, that protons could actually bind.
Right.
And so I have one question and then one comment. When was that established? Because I've been on fundamental research now since 75. But as I pick up on little odds and ends of the work that Stephen Hawking has done over time, one of the most recent ones on quantum dynamics and so on, my feeling is that creation is continuous. And there's an analogy
Okay, so the first question, first of all, how do we know, you didn't ask this, but this is sort of like part connected to what you asked. How do we know that if the strong force were 25% weaker, it's hard to be precise, 20 or 25% weaker, that deuterium, a proton and a neutron wouldn't stick? Well, that's based on just solving the equations, and you just simply make the potential well a little bit shallower, and you solve the equation and it doesn't bind. And in the same way, you can show that if the internucleon potential were a little bit stronger, the diprotons would bind. Diprotons come very close, two protons come very close to binding to make what's called a diproton. It only misses, I think, by a small fraction of an MeV. They're very close to binding. So I forget the exact number, but I think if the strong force were a little stronger by 1% or something, some very small fraction, the diproton would bind. So that's very important. So in the sun, what the consequences of that would be is very hard to work out, and I don't know that that's been definitively worked out. But how does fusion happen in the sun? Well, the way hydrogen burns in the sun, you have a lot of hydrogen nuclei, protons. They don't just fuse. What happens is one of them has to turn into a neutron by a weak interaction process. The proton converts into a neutron plus some stuff, and then the neutron binds with the proton. That makes the process rather slow because the weak interaction process of turning the proton into a neutron takes a while to happen. That's a slow process. And that's one reason that the sun burns for a long time. The sun will last for a total of about 10 billion years. That's because that process is slow. On the other hand, if a proton didn't have to turn into a neutron to bind with another proton, we could just directly bind with it through the strong force, that's a very much faster process. Orders of magnitude faster. Now, at first, back in the day, people would say, well, then the sun would burn not in billions of years, but would burn extremely rapidly in hundreds of years or something. And then we wouldn't be here because the sun would burn out so quickly that we wouldn't have time to evolve. But then it's much more complicated, apparently, because, yes, but what would happen is the different types of stars would arise. They're very different from the sun. But you could have stars that lasted for billions of years. They would just be very different from the sun. They're very different from the sun. So it's not at all clear how that cashes out in the end as far as the possibility of life. But it certainly makes it questionable whether life could arise. But it's basically just by solving the equations. That's how we know. As far as continuous creation, I mean, from the traditional Catholic point of view, from the point of view of God, creation is an instantaneous process. God doesn't undergo change. God is outside of time. God doesn't learn new things and forget other things and change his mind and all of that. God is completely atemporal, and God, in the traditional understanding, created the whole universe in all of its parts, throughout space, all the temporal and spatial parts of the universe, in one timeless act of creation. God, just as God knows all things in one timeless act of knowing, and he causes the world in all of its parts in one eternal, in the sense of non-temporal, act of will. And so I don't know what it even means to say creation is continuous. God willed the whole universe in one act of creation from all eternity. Oops. It was like that. It was happening like that. So, yeah. So God is, in a sense, creation is happening all the time because creation is God conferring being upon things that exist. So the fact that this phone exists right here and now is because God is conferring being on it right now. It has being now because God is the source of its being. So this is right now, as it were, being created. Everything that exists is, in some sense, being created at that time that it exists. But of course, from God's point of view, he wills it all in one act of creation. He doesn't undergo change. But yes, so God doesn't just create, 14 billion years ago and then sit back. We say in the Creed, God creates all things, visible and invisible. All things are created by God equally. And a good analogy is the author of a novel. The author of the novel creates the whole novel. So he equally writes the words at the beginning and the words in the middle and the words at the end. Every word, every letter in the novel is equally created by the novelist. And everything in the universe is equally created by God. So the act of creation is, everything is being created by God. So I don't understand the point. In a sense, I've never been a big fan of Teilhard's. Maybe that's why I don't understand.
Questions? Anybody really?
I'm sorry, I can't hear from back here. Yeah.
I didn't quite get your counter arguments today given the multiverse and Newton's limit of finality.
That the multiverse would be what?
Newton's limit for continuing finality. The multiverse.
It does. If every you can certainly, I mean, it's certainly conceivable you could might be able to explain some of the fine tunings if we live in a multiverse. I agree, but I don't have a counter argument to that. But I'm saying I'm saying that if for the universe to be a multiverse requires the truly fundamental laws to be very special.
Because it's the only way to combine gravity and
To say that the fundamental laws are for hundreds of years, people had assumed that if you measure the mass of the electron, it's the same everywhere in the universe. It's a constant of nature. That's sort of what you expect. The proton has a certain mass. I measure it today, I measure it tomorrow, I measure it here, I measure it in Japan. It's a constant of nature. It's kind of a new idea that things we have traditionally thought were constants of nature, like the V, like the strength of the strong force, and so on, that they might actually vary from place to place. We see no evidence of that in the part of the universe we can see. You look to the farthest reaches of the observable universe, billions of light years away, and we can see that electrons have the same mass as they do on Earth, that oxygen atoms behave just as they do on Earth, that everything seems to be obeying the same laws, the parameters have the same values. It's a kind of a strange idea that some of these parameters actually vary from place to place in the universe. That's not what you'd expect necessarily from any old fundamental laws of physics. You would have to have the fundamental laws of physics be of a very special type so that basic parameters varied from place to place. It's not something that necessarily ought to happen or that you would expect to happen. We do know examples where that can happen, at least for some parameters. I gave an example of the simplest supersymmetric granular pipe theory, that there's certain parameters that would vary from place to place in that particular theory. But anyway, that's all I'm saying is that in one way or the other, the laws, the fundamental laws, have to be special, either to have a multiverse, or if you don't have a multiverse, if you have a more traditional kind of universe, they have to be special in these important parameters having just the right values. In a sense, and you can't quantify this, but if you were sitting down and advising God on what universes to create, and you cooked up some laws of physics, and by the way, that's what people in theoretical particle physics do for a living, is you cook up a lot of them, model building. You cook up laws of physics, and you hope that one of them actually turns out to be the laws of our universe, and then you get a big success. And most of the time, they're not the laws. They turn out to not be right. But if you're sitting there and you're cooking up possible laws of physics and saying, God, why don't you create this kind of universe or that kind, chances are the ones you cook up are not going to give you a universe that has living things in it. That's a very remarkable thing. And that's what both Hawking and Witten are saying and many others are saying. We should be surprised, in fact, going back to the beginning, the fact that the laws of physics have the right features to give rise to life, as Witten said, will never resolve the sense of wonder about that. You shouldn't take that for granted. Because, all right, you build a universe with some laws and yeah, there'll be some kind of living things in it. Everything we know suggests otherwise. That you have to have something very special for that to happen. It's not something you should take for granted. That's what I was going to do.
Okay, so I'm not a physicist.
Yeah.
And I'm very intimidated by most physicists throwing around words like the universe is vastly bigger than, what we imagine it is. Because someone has to run the numbers. I mean, as a biologist, I know enough about probability to know if V can assume theoretically, 100 values or 1,000 values. Okay, and V is only one of 100 parameters, each of which can assume 100 values.
Mm-hmm.
You start to vanishingly small probabilities. I mean, many, many, many times.
You mean, so even no matter how big the universe is, to win the lottery is going to be very hard.
So what would be the probability of something as big as the visible universe? How big would the actual universe have to be?
It would have to be quite enormous because, take the parameter V as a good example. So in the standard model of particle physics, actually V is not a fundamental parameter, but it directly comes from fundamental parameters. But it's more convenient to talk about V. If you ask what values of V are mathematically possible, that is, outside that range, the theory doesn't make any sense and it breaks down mathematically. Well, it turns out V just a priori, just for the theory to be mathematically self-consistent, V can lie in a range of 57 orders of magnitude.
Well, there you go.
And the window, I forget, this is my paper, but it was written 20-something years ago. The range that it can be is, I forget, is probably an order of magnitude or two. It may be much less than that. Actually, if V is bigger already by a factor of 1.4, if V is 1.4 times what we see it to be, already disasters occur. So it can be somewhat smaller without any obvious disaster occurring. But it's actually compared to 57 orders of magnitude on a log plot, it's a very narrow window. And as Maureen said, Professor Condick said, as Maureen says, if you then take other anthropic coincidences and what are the chances that, how finely tuned do they have to be, and you multiply all those together, how many lottery tickets do you have to buy? Okay? And the universe has to be some now, it could be, now here's, and that's a good argument. However, I should say that we don't know at the moment, as far as anything we know is concerned, the universe actually could be infinitely big. In fact, given what we know about cosmology, there's a parameter in cosmology that if it's bigger than 1, then the universe has a finite volume at any time after the Big Bang. And if it's less than or equal to 1, the universe has an infinite volume. And as luck would have it, and actually there's a reason for this, it's right at 1, and we can't tell whether it's a little bigger or a little smaller. And we will probably never know, therefore, whether the universe is infinitely big or finite. So it could actually be infinitely big, and that would solve that problem. Because if you have an infinite number of lottery tickets, you're going to win, right? If they're random. So that's good, but it's a good point. It's probably a dauntingly big number of regions of the universe that you would have to have for everything to line up just right.
Yep. 2 more adult questions.
I
Angela?
just had a question or a statement. It seems to be a circular argument because we're here, therefore those things have to be that way.
Sure. I'm not sure what the argument, there could be a circular argument, but I don't think I made a circular argument. I'm just saying that I mean, if you walked outside and there were 1 million bullets whizzing around and they all missed you, you might think something was going on that required explanation. Or suppose that the wind was blowing and howling and all the leaves were blowing off of all the trees in your neighborhood and they landed on everybody else's lawns, but not a single leaf landed on your lawn. Then you say something's going on here. And I don't know if that's a circular argument or not. But if it turns out that there are a lot of aspects of the laws of physics have to be just right for us to be here, that's amazing. I mean, I agree with Whitten. It's an amazing thing to get these things all lined up. Yeah. Of course they did, or we wouldn't be talking about it, but it's still amazing that they did.
Arnie, did you have a question? Did you have a question?
Is that it? Okay.
And now we have student questions.
Oh, is that the student? He can whisper it to you, and then you can relay it to me.
Andreas has a question.
Why is my voice so loud?
What's your question?
Ask your father.
What's your question? What's your question? Tell me your question. Tell me your question.
Do you know it? If it's a question of, like, why is that strange man up there saying strange
You
things?
should ask that question.
Well, you ask it for him. Come on.
Okay.
Ask it for him.
Are there people far, far away from us right now who are fighting for us in the universe?
Like, other than angels, for example?
Do angels
I
count?
don't know. But if there are people far, far away, I sure hope they're fighting for us and not against us. But the good news is, I think most people, physicists would say, if there are intelligent aliens out there, they're probably so far away that we'll never encounter them. So that there's very, very strong reasons to doubt that they're close enough in time or in space for us to encounter them.
Does that make you feel safe?
Yeah, so we don't.
Is there another student question? Your parents to ask? You know their question?
I have a question. Have you seen Galaxy Quest? Oh, you have seen Galaxy.
Well, let's thank Steve. You have to clap. You have to clap. He answered your question.